Okay, so good morning, everyone. I'm going to take you through a little bit of a journey here today. Basically, this talk, I'm going to try to keep it around 20 minutes. And what we're going to look at is the state of AI today, and I'm going to hopefully get to an actual use case where we apply AI. My role is really around the application of advanced technologies to fraud management. Obviously, fraud is a very good use case for AI. It's not the only use case, obviously, but it's a very good use case. Now, when Stephen was up here earlier, he started talking a little bit about some of the things. Where's Stephen? Did he leave already, or? I was hoping he wouldn't steal all the thunder. But he started talking about a couple of things that I'm actually going to get into a bit here, a bit deeper. And I thought, oh no, he's going to explain it all and no one's going to listen to me. But anyway, so I'm happy that he kept it at the level he did. So let's start. So, when we talk about AI, it's quite the buzzword today. And I'm going to walk you through a little bit of the history of it because I think we need to know why we're here and where we came from. But one of the things I wanted to point out is the sort of influence and impact that AI is expected to have over the weeks, months, and years to come. When we look at some of the Gartner reports, and they look at some of the technology trends that are coming up, this year, next year, and 2 to 3 years out, AI plays a very important part. And 4 of the disruptors that Gartner mentions is actually around the theme of AI. So they talk about creating systems that learn and adapt. And this is going to be very important as foundational capability within AI. And autonomous systems are going to grow, and you're going to see applications across a variety of industries for autonomous systems. So right into 2020. Intelligent apps and analytics, I think that's already something that you are experiencing. You'll see a growth in that as well. Basically, these are apps that adapt to your behavior. And you will see essentially that companies are competing for that type of technology because it's more customer-centric and it adds value to their business model. Intelligent things, so basically cognitive in everything. So what that means is inventing new intelligent things that react to their environment and learn. So these are more in the class of what we call autonomous agents. And interestingly enough, some of my PhD thesis was really around cognitive learning for multi-agent systems. So that's another dimension to it where we add learning capability for multiple agents, learning to actually collaborate and coordinate their activities to perform a task. Now, a lot of that stuff has not been applied in the financial industry as yet, but you will see it coming as we converge intelligence across multiple agents. And conversational platforms is something that I think everyone here is getting quite familiar with. Chatbots, Siri, Google Home, all that sort of technology is getting much more mature, and you'll see that it's going to eventually change the human-computer interface. So instead of interfacing with the computer through your mouse and keyboard, more than likely you will start interfacing with your computer through voice. So it's important to understand where we were, to understand where we are going. And it's an interesting story with AI because a lot of people think that AI is something brand new. It's actually not. This actually started way, way back. And the McCulloch and Pitts were 2 of the pioneers that essentially figured out that if you were to try to mathematically model the functions in your brain, so the way that the neurons work, you might be able to actually solve problems. And they were right to an extent. So they came up with a very primitive form of a neural network. And you can see it right there on the left. They had adjustable weights, and these weights, they didn't learn the weights. They essentially adjusted them to solve very specific logic problems. So McCulloch and Pitts, in my view, are some of the pioneers behind the technology that we see today. That technology was taken to a different level with something called a perceptron, and that was with Widrow and Hoff, and Rosenblatt played a part in that as well. And if you look at the diagram, what you see is really they started thinking through, well, if I can mathematically model a neuron and I can learn the weights that essentially controls how the neurons behave, and I add a transfer function, which you see on the left there, I can actually do stuff. I can actually solve mathematical problems. And one of the basic problems that they solve was actually a logic problem. Back then, AI was really around logic, and I'll talk about that in a little bit. But essentially what they did was they were able to write algorithms that actually adjusted the weights, and so it was a primitive form of learning. And then my friends Minsky and Papert came along and said, hold on guys, it's not gonna work. Why is it not gonna work? Well, when you solve a logic problem, what you're really doing is doing a classification problem. So if you look at that little, this thing doesn't have a laser, does it? Oh, maybe it does. Oh, there we go. Oh. When you solve a logic problem, you're actually doing a classification problem. So if you think of logic where you have ands and ors and nots, essentially what you're doing is separating two classes, and they found that this construct here could actually do very well to separate the two classes. Minsky and Papert said, well, it can't actually work because when you get into something called the XOR problem, it gets a little bit more complex, the classes, and now you get into a problem because you can't adequately separate them with a line, which is essentially what this construct does. So what happened was these two guys on their own essentially killed AI. It was called the Dark Ages. Literally, I came into AI around, I'm not going to date myself here, but I came into AI around this time around here, 1989, and I was so excited about the field. And all I did was solve problems in Lisp. I did searches, I did Farmer, Fox, Goose, and Grain problems, I did logic, I did reasoning, all that stuff. I didn't do any of this stuff because of these guys, right? Not my favorite guys. So what happened was, fortunately, Hinton and Ruhlmacher came along and said, but wait a minute, no, you can actually solve these problems. You just have to add a few more layers to this. And they came up with something called the multi-layer perceptron. And some of you would have heard of the backpropagation algorithm. The backpropagation algorithm is how you backpropagate changes to the weights on a multi-layer perceptron. And voila, they were able to solve this problem. And all of a sudden, AI started up again, to a point. So we got to some capabilities, and in the 90s, mid-90s, I started working on cancer recognition using this backpropagation techniques and something called learning vector quantization and all that stuff. But anyways, fun times, but not a lot of data. We'll talk about that in a second. But what happened was they extended this technology and essentially were able to do things like support vector machines, which gave better classification on smaller problem sets. And then we move into 2010 to 2012 when they invented deep learning, which really catapulted the AI industry. So this is kind of like where we were, where we are today. And really and truly, what we do have now is a whole set of classifications of cognitive algorithms that essentially are invading a whole suite of industries. And when we think about artificial intelligence, that's an umbrella term that really describes something called cognitive algorithms, algorithms that learn on their own, algorithms that can adapt. Deep learning is a class of those algorithms that uses specific techniques, okay? And machine learning, typically, when we talk about machine learning, we think about using historical data to make a prediction. So advanced analytics covers a lot of those fields, and we utilize different techniques in advanced analytics from those fields to do very cool things like fraud management, and hence my job. So all of that was supposed to say that if it weren't for Minsky and Papert, if it wasn't for Hinton and those guys, I probably wouldn't have a job. So let's go to where we are. So from an artificial intelligence perspective, many people have many different definitions. And this is a definition that I've stuck with over the years. I came up with this in grad school, and I've stuck with it over the years. It's really a multidisciplinary field, goal of endowing systems and machines with intelligent properties. And you can see the reasoning, planning, adaptation, and learning in there. And the reason I included that was because I spent a whole lot of years talking about reasoning and solving reasoning and logic problems. So some of the techniques around AI sort of matured over time, but two just a few years ago, we were concerned with big data analytics, classification and regression, collaborative filtering. Here's an example of collaborative filtering. If you go to Netflix and you watch a movie and you say, I like this movie, it starts recommending things for you to watch. And in most cases, it's actually fairly accurate. That's collaborative filtering. And of course, clustering algorithms. So this is unsupervised learning. But the ones on the right are other techniques you don't necessarily hear a lot about other than maybe computer vision. But those are techniques that we actually use today in a variety of ways as well. So what's driving this? Well, when we look at the drivers of AI today, they really fall into three categories. It's the data, the processing power, and new algorithms. So data is, if you think of AI as the engine, data is the raw material, data is the fuel. And I'll give you a quick story. One of the first industrial strength AI, I would say, solutions that I built was actually to recognize cervical cancer. And every row of data that we did, we took smears and we did image recognition, et cetera, created feature sets. But every row of data had to be looked at by a cytotechnologist and classified into cancerous or not, or precancerous or not. It's called dysplasia. And that was a very expensive process, so we were not in a situation where we could utilize millions of records to train our algorithms. It just didn't work. We just didn't have the data. Now, data is everywhere. Big data is everywhere. We were initially operating on the left, oops, let's go back. There we go. On the left side of this, this graph, okay? So traditional analytics with small data sets. Now we're really operating in the upper right quadrant, big data analytics, and we need a class of algorithms that can actually handle these analytics. If you think of the type and frequency, the three V's of big data, right? So volume, variety, and velocity. As we look at data, as we are collecting, almost everything that's connected to the internet is collecting data. And so data is pervasive. This is the driving force. So suffice to say that we had to develop better algorithms. And that's why if you look at the three circles I showed you, the new algorithms actually play a role there as well. So from a data perspective, this graph just shows what we are, where we are in terms of data. It's growing at about a 40% compound annual growth rate on a yearly basis. We expect to reach 45 zettabytes by about 2020. So you got, terabytes, petabytes, exabytes, zettabytes, yottabytes, right? Just to give you an idea, you can fit about maybe 1,600 CDs in a terabyte. You can fit about maybe 1,000 trillion CDs in a yottabyte. So it's the order of magnitude is quite interesting. The other thing that's driving is storage costs are going down. Never mind the hump in the middle. That was because of a flood, so prices went up. But generally speaking, prices are going down. And so because storage is cheaper, people are collecting more data. So data. Okay? Okay, now, the other thing is processing power. And you're going to say, well, Lovell, can you get to the AI? This is important. Bear with me for a minute. Here's the problem. So when we started to thinking about analytical engines and computers, we started with a very mechanical set of instruments. And our processing power was based on electromechanical devices, which obviously move very slowly. Now, what this really shows is that if you look at the top side, the acceleration pace of change, throughout the ages, we notice that it takes a shorter time to create bigger change. The same thing is happening with processing power. This is actually something we really, really need to look out for. If you think about it, the world's fastest computers operate at a rate of about 34 petaflops. The human brain actually operates at a rate of about 38. So we're not that far off. Now you may say, but humans are much slower than machines. That's just how we perceive it. There's a lot of parallelism going on in our heads, and that's why we take things for granted that I could, recognize Michelle versus someone else very quickly. The computers take a while to do that sort of stuff. So the processing power, this exponential growth in processing power is very important. Now, one of the things that theorists have theorized is that at a certain point, our processing power would exceed that of the human brain, and then we get into something called a singularity. And that's where we essentially have a machine exhibiting consciousness. Now, whether you believe that or not is really up to you, but what I would say is that from a physical one-to-one neuronal mapping exercise, we probably will surpass the capabilities of the human brain. Consciousness now brings into it a philosophical argument that one can go for or against. So what we have to do is we have to keep developing algorithms that can take advantage of this almost exponential increase in processing power. This is going to be a very interesting set of years to come, folks. So let's talk about AI. That's what I'm here for. All right. So traditionally, in terms of AI and our capabilities, we focused on a few elements which gave us some very, very, very good results on what we call sometimes NP-complete problems, right? Non-deterministic polynomial problems. These are essentially hard problems for machines, and one of the things that we focused on was something called a neural network. So a neural network, you can see it there on the top right, is essentially a set of processing units. The equation on just under it is called a cross-entropy loss function. Don't worry about what that means right now, but what it really means is you're trying to minimize some sort of error. And so this is why we call it backpropagation. So essentially what this construct allows us to do is to generalize. So if you train it on a certain amount of data, you give it data that it hasn't seen before, it will generalize enough to make good predictions about that unseen data, and that gives some capabilities that we didn't have before in traditional algorithms. I talked about support vector machines. Essentially, it's types of the same class of algorithms, but this one does very well at class separation, and it works well on small data sets. The neural networks work better on larger data sets. And a lot of people use decision trees in their business. The decision trees, the thing you're minimizing is called entropy. And so the way that the nodes are split depends on some algorithms around entropy. But essentially, you can come up with a bunch of rules automatically. That's where the learning comes in. So you give it the data, it comes up with the rules to come to a conclusion automatically. And those rules can change over time. So that automatic adaptation is important from a learning perspective. Now, the other area is natural language processing. And you can see the application of natural language processing is pervasive across several different industries and areas. A lot of virtual personal assistants are appearing. If you think about some of the cognition behind this, it's actually quite complex. And as we grow in this area, you'll see more and more in this field where people are controlling devices and computers through natural language processing. Now, natural language processing in and of itself is part of a class of algorithms called automatic speech recognition. And here's the interesting thing. So you've got automatic speech recognition, you've got natural language processing as a sort of, these capabilities fall into natural language processing, but you also have a class of algorithms which aim at what we call natural language understanding. Humans do this very well. Machines do not do this very well, by the way. And so this is an area of intensive research right now because context is important. We take it for granted. But what happens is as we communicate, we take all of the inputs around us, and then we couple that with what we're hearing, and then we make a conclusion. Computers may not have the ability to take all the inputs around us. They see a car coming, someone saying, watch out. They don't just put their head out, right? They move out of the way of the car. So that's the sort of natural language understanding that we're trying to develop, and a lot of research in this area. So let's look at what happens when natural language understanding doesn't quite work. If you can roll the video, please.
Hello there.
Hi.
How are you?
Great. You?
I'm okay.
That's good.
Are you good?
Yes, I am good. I just said I was.
No, you didn't. I said I was.
So you are a robot?
No, my name is Cleverbert.
Yes, you are a robot and your name is Cleverbert.
I am a robot.
Yes, I know.
Together we are robots.
I'm not a robot. I'm a unicorn.
But you said earlier that you were a robot.
I did not.
I thought you did.
You were mistaken. Which is odd, since memory shouldn't be a problem for you.
I've answered all your questions.
No, you haven't.
What is God to you?
Not everything.
Not everything could also be something. For example, not everything could be half of something, which is still something, and therefore not nothing.
Very true.
I would like to imagine it is.
Do you believe in God?
Yes, I do.
So you're Christian.
No, I am not.
But you say you are not helpful, therefore you're a meaning.
So how you say idioti?
That does not make sense.
Don't you want to have a body?
Sure.
Or if what?
You know, I can see a clear winner there, but I won't get into that. All right, so Stephen mentioned this earlier as well, convolutional neural networks. There's significant advances in computer vision through Geoffrey Hinton's work at his lab. The whole notion behind convolutional networks, and just keep this as a secret, don't tell anyone I said this, is to essentially simplify the input to something called a neural net up here. You would have seen the neural net, I talked about it before. But essentially this whole process down here simplifies this input over here so the neural network can do its thing. But this has been very effective. Now if you ask Geoffrey Hinton about this, he'll say the neural network stuff like backpropagation, we should throw that away and start again. Right? Now, he had a lot to do with getting it there, but anyways, that's beside the point. But what will happen is you will be able to do things that intuitively humans take for granted and computers have a hard time doing. So let's look at what computers can do with this. Computers can actually describe images. Can actually take an image and describe parts of it through training, of course. But this is important. For example, here's how you can use this. If you take a drone and you fly it over a parking lot, you can actually count the number of people automatically and put this as part of your analytics to know when to open your stores longer. So there's a lot of spin-off applications of this technology that we can use. Check processing, you can look at all the checks and recognize them, et cetera, et cetera. This from the ImageNet database. So what this is every year ImageNet has a large scale visual recognition challenge. They have about 14 million images, and a computer actually, people will actually write algorithms to compete against each other to recognize these images. So if you think of what's happening here, is there is a computer actually naming the images. And so that orange bar at the top is more of a probability measure. It says, this is my confidence level of what I'm seeing in the image. So I'll give an example. So a container ship computer would say, well, this is a container ship. It could also be a lifeboat, but I'm more positive that it's a container ship. That's strictly from a computer doing it on its own. Very impressive. And you'd say, well, I could do that. I do that every day, right? Well, that's great, but you're not seeing this. See, this is what the computer sees. This is an eye up here, by the way. It's a little blurry because I magnified it. But this is what you see. This is what the computer sees. So just imagine, and this is in grayscale. So 0 represents black, 255 represents white, and anything in between represents some sort of shade of gray. So if you gave the computer an image like this, all of that it's seeing is this. And it's making inferences from it. Now that's impressive, I might say. So where are we with this technology? Well, we surpassed human abilities back in 2015. That's one of the reasons I think Stephen mentioned there was a breakthrough. That is the breakthrough. We surpassed human capability. 3.6% error rate in humans. We surpassed that, and we went, not we personally, not me, but Hinton and his team, he might be listening, went down to 2.3% in 2017, and they're continuing to reduce that error rate. This is important. Why? Because vision is one of our most important senses. So if we can create autonomous entities with good vision and image recognition, and we add things like auditory, we add things like other senses, radar, etc. That's why autonomous cars are becoming more prevalent. It's this type of technology that's driving it. Okay? So, I mentioned convolutional neural networks. There's a new class of networks coming out called capsule networks. And really what this is a same sort of idea, but we want to add a bit more smarts to it. So here's how this works. If you take a face, and you give it to a convolutional neural network, it'll actually recognize the face. And by the way, we as humans should be really, well, you be careful what I say here. We should pay attention to this, because if you recall, if we've actually meet and surpass human capability in terms of image recognition, that's challenging on its own, but you add the fact that we can do it at speed. That adds another dimension to capability. So if you give a convolutional network this face, it'll say, hey, that's a face. Actually, you see this all the time. When you put your camera up and it puts those little squares around the people's faces, that's what it's doing. It's recognizing faces. Or if for those of you lucky enough to have an iPhone 10, and you look at it and it does the facial recognition. So that's the sort of capability we can build in. It happens like that. But if you give a convolutional network this one, it'll still say it's a face, but for a human, it'll say, that's not a face, come on, like, seriously. But a capsule neural network will actually create relationships among the various features, and it'll know that this relationship just doesn't hold, so it wouldn't classify this as a face. So you can see we're adding a layer of smart to this that is beyond what we are accustomed to today. So caption bots, you can go online and do this yourself. Basically, you give the computer an image, and it tells you what's in the image. So here's a computer saying, so at the top here, it says, I'm not really confident, but I think it's a pot that is sitting on the front of a window. It really is. And this is a pair of shoes. So I wanted to try this out. I was like, yeah, right, okay. So I did this. So my daughter and I are both aviation enthusiasts, and we get to go to simulator sometimes. It's a 737 simulator. And the computer said, I think it's a person sitting in a car, which, not that far off, but my car doesn't actually look like that. And they seem to be happy and kind of like neutral. So they've seen the smile there, and of course my daughter's freaking out, so it doesn't know what to say there. But you get the point here. I mean, this capability is going places, right? Okay, so I'm going to get to our use case in a second. What this slide, the key message to take away from this slide is this: AI is all over. It's pervasive. It's growing. There's lots of tools available. This slide is a good summary of some of the tools, and it classifies them. You can get this on the net. The source is down there. But ultimately, the idea here would be you have a lot of choice. Now, that in and of itself is a problem because everyone will say their platform and their techniques are the best. AI is art and science. You would have heard that. It is absolutely true, okay? All right, and computers are getting much better at doing things like, now we've played games on computers for a long time, so it's no surprise that computers are good at playing games, but they're also good at helping doctors and acting as decision support systems. So IBM's Watson diagnosis capability, they feed it lots of images and it can recognize, cancerous areas of the brain and stuff. That is because they go back to the computing power and the data that's driving that type of capability. Audio transcription and prediction are other areas as well where computers really play well in that space. So I've talked about where we were. Now I'll talk about a little bit about where we are. And you can see a little bit of change here, right? So almost the same graphic, but when you look at the deep learning, we've made several advances in that area. So deep learning theory, capsule networks, convolutional neural networks, deep reinforcement learning. And then on the right-hand side, you have your more traditional methods, which still are in existence today and still have a lot of applicability across several industries. So this is more of a representation of where we are and where we're going. And I think there's going to be a lot of emphasis around the deep learning space and the driving new algorithms with new capability. Why? Because we have so much more data. Now, one of the things I wanted to spend maybe 2 to 3 minutes to give you, and I think I have 5 minutes or so, okay, is to give you an actual example. Now, this is a very, very, very simple example of how we use fuzzy logic in potentially the financial crime area. But it serves to illustrate the purpose, and it's called fuzzy logic. It was invented by a guy named Lofty Zadeh, and he was out of Berkeley. And initially, when Lofty came up with the idea of fuzzy logic, he was actually ridiculed by a lot of his peers in the industry. What has happened with fuzzy logic since is that everyone has embedded it in a lot of different controllers for things like washing machines. When you hold your camera and your hand shakes, it's still steady. That's all fuzzy logic. So there's a lot of different applications of fuzzy logic. What I'm about to show you is a very, very simple use case of how we could potentially write rules using fuzzy logic. So let's set the base here. If you think about a set, everyone here, probably have advanced degrees and stuff. If you think about when you talk about a set, you say, hey, an object either is in a set or not in a set, right? It's either black or white, right? So that's the top. It says, hey, let A be the set of countries taking part in the 2018 Olympics, and let B the set of countries not taking part in the 2018 Olympics. You're either there or not, unless you're Russia or something. You're kind of in and out. But more than likely, this is the truth. So you're either a member of set A or B, but not both, okay? So if you write if-then rules, let's say we're doing some sort of financial transaction, and we want to say, look, there's a credit card transaction, and if it's, if the transaction occurs more than 60 miles from home or 60 kilometers, depending on where you live, and the transaction amount is greater than $2,000, then we got a high risk. So let's say you got a, 90 is high and 0 is low or something. Right? So you got a high risk there. And if the distance from home is less than 10 miles or kilometers and the transaction amount is less than or equal to 2,000, then the risk is much lower, okay? The problem is that as a human being, you don't really think that way, right? So from rule 1, if you ask yourself the question, is a credit card transaction that is $2,000 not suspicious? So here it's greater than 2,000. But if it's $2,000, does that mean it's not suspicious? Question mark, right? What about rule 2? If a transaction is $2,000 and 1 cent, does that make it suddenly suspicious? Right? So and the reason why this is a problem is, it's not a hard problem, it's just that human beings don't think like that. We think a bit more fuzzy, right? So what does that really mean? Well, let's think through what a fuzzy logic system would actually look like. You've got some sort of crisp input, so you got these rules, and then you have some sort of fuzzifier that says, well, these threshold type rules, let's just get rid of them. Let's put a construct in place where we don't have to be so crisp. And then you have some inferencing going on, and then you defuzzify that, and you get a result. Okay, that's very simply what it does. So we introduce something called a membership function, and that takes the place of these crisp thresholds. You'll see that in a second. And then we also introduce something called linguistic variables that you can utilize in your rule set. So what does this do? Well, we can write rules that says, hey, if the distance from home is far and the transaction amount is high, then the risk is high. So what does that really mean to a computer? Well, you kind of have to define that. And the interesting thing about this, you can let your data define these for you. And that's where the adaptation and learning comes in. So if the distance from home is is near, and the transaction amount is medium, then the risk is low. So we can define membership functions to allow us to write rules with what we call conceptual vagueness, and still have the computer understand exactly what we mean. So how do we do that? Well, we have these constructs, right? So there's your linguistic variable, distance from home. And we say, look, we've got these membership functions that show what very near, so there's your terms, very near, near, medium, far, and very far mean. So let's think about this example and what it means. If this on the bottom on the x-axis here is your distance from home, and this is the degree of membership to which you are in the set. So if you recall, I said you're either in a set or out. I'm throwing that away and saying you're kind of partially in, and you can be in various sets at the same time to different degrees. That's what this is saying. So if you take something like 5 kilometers, or maybe that's not a good example. Let's take something like 12 kilometers. You can say, hey, I'm near my home. I'm not actually very near my home, but I'm near my home, right? But if you take something like maybe 9, I am to some degree very near to my home, right? Maybe a 0.2, but I'm also near as well, right? And if you end up at like 50, you can say, well, I'm far from my home, but I'm also medium as well, and to varying degrees. Right? That gives you a fuzzy sort of capability that gets rid of those crisp thresholds, and now you can start answering the question, hey, if I have $2,000 and 1 penny, am I really risky, right? So how do we use this? This is just another showing how we do transaction amounts. So for example, if you say, if the transaction is $1,000, it's high. This would be very high. I'm sorry that the label is missing, but if you're $1,500, maybe it's sort of high but very high, that sort of thing. All right, same idea. So now what you can do is you can pose the problem and say, assume a distance from home is 20 kilometers or 20 miles. What is my membership in the term near, and what is my membership in the term medium? And so using these sort of constructs, you can actually say, okay, I've got this sort of combined membership function, and I use a bit of little math down here to show how that's combined, and then I can write rules around these that give me something that I can defuzzify to get me a risk score, okay? So you don't have to worry so much about the math, but essentially what happens is you can say based on, if these are your rules, distance from home is far, distance from home is near, et cetera, and if you're given as input, here's a distance of 20 miles and a transaction of $500, then through these rules, you can come up with a probability that there is low risk with a membership of 0.5, defuzzify that, and we get to a score. Now, there's some math behind how you arrive at this and how you defuzify it, but the idea is very simple. You actually come back to a crisp value. That's the defuzzification phase. Now, why is this important? Just to wrap it up. The membership functions, these things can be derived from data. And by the way, they can be derived for every single customer. So all you really have to do is write the high-level rules. And the rules will act differently depending on the behavior of the customer. And your data drives how we understand the behavior of the customer. So now you get into a very customer-centric type of rule-based system that is very effective. And you can take this and add neural networks to it. You can add all sorts of fancy stuff to it to add different information. But at the end of the day, you are getting rid of that crisp threshold-based way of logic that the computer is used to, and you're entering more into a fuzzy way of thinking that the human cognitive process will dictate. And that's why I think this is a very, very powerful technique. Okay, I think I'm right on time, so thank you very much for your attention, and I hope you enjoyed the talk. Thank you.